Hello there, and welcome. I'm glad you've arrived. Maybe your day has been long and your thoughts are still turning, or maybe you're the kind of person who drifts off best with something vast and strange to wonder about. However you found your way here, I'm glad you did. You don't need to do anything now but rest. Let the tension fall from your hands. Let your eyes soften. Let your breath slow, like the quiet curl of space around a star. Because tonight, we're not just gazing at the sky, we're falling through it. We're going to explore black holes, not just what they are, but what they do, what they hide, what they challenge. These aren't just heavy objects in space, they're the edges of understanding, the silence at the heart of everything. Some of what you hear tonight might sound impossible. Some of it is, but that's the point. This is a journey into the most mysterious, powerful, and mind-bending objects in the known universe. Not to conquer them, but to float beside them, to feel their pull, and to dream within the gravity of the unknown. They are not holes. The name is misleading, as names often are when something exceeds our ability to comprehend it directly. A black hole is not an empty space or a tunnel or a gap in the universe. It is the opposite, a place where so much mass has gathered into so little volume that the gravity becomes absolute. A single black hole can contain more mass than millions of suns, but instead of spreading that mass across light years, it is packed into a region no larger than a city, a weight so intense it pulls even light into silence. And yet, from far away, it looks like nothing, just a void, a shadow that doesn't move, doesn't flicker, doesn't glow, not because it's empty, but because everything it touches is taken. Light, time, matter, all drawn inward and never seen again. What we call the event horizon, the edge of this strange place, isn't a wall or a surface. It's a boundary in space, a quiet line where the rules change, a threshold. Once you pass it, no force in the universe can bring you back. But if you were falling toward one, you wouldn't feel it. There is no bump, no flash, no sensation to mark your crossing. You would drift silently across that line, unaware that your escape has become impossible. From the outside, however, the story is different. To a distant observer, it would look as if you were slowing down, redshifting, fading, frozen, just above the edge. Time would seem to stop. But to you, it would continue, second by second, as if nothing had changed. Falling into a black hole would feel normal, at first. This is one of the strangest truths about black holes. They don't pull like a magnet or suck like a vacuum. Their gravity obeys the same laws as anything else in the universe. If our sun were suddenly replaced with a black hole of the same mass, Earth's orbit would remain exactly the same. The sky would grow dark, but the planet would keep circling in silence, unaware of what now anchored it. Gravity does not require light or heat or explanation. It simply is, and yet, when mass collapses enough, gravity begins to do something more. It begins to bend the shape of space itself. A black hole is not just a massive object, it is a distortion, a pit in the geometry of the universe. Not carved, but curved. Anything that moves nearby will find its path warped. Light bends, time slows, orbits tighten, and if you move too close, escape becomes impossible. Still, the name endures, whole, as if there is something to fall through, but there is no bottom, no tunnel, no hidden exit on the other side. What lies past the event horizon is not a passage, but a deepening, a compression. The closer you approach the center, the stronger gravity becomes. There is no floor, no surface to crash into, just more inward. At the very heart, if current theory holds true, there is something called a singularity, a point of infinite density, where space and time collapse together and the known laws of physics lose meaning. But we don't know for sure. We can't observe a singularity directly. We can't send signals out from inside. Everything we know about black holes, we know from the edge. From the event horizon, from what surrounds them, from the way they influence the things they haven't yet consumed. The idea of a singularity comes from the math, not the telescope, and even the math begins to break down under such pressure. What's remarkable is how calm everything seems until it isn't. If you were to fall into a supermassive black hole, the kind that anchors a galaxy, the tidal forces at the event horizon might be surprisingly gentle. Your body would remain intact. Your thoughts would continue. You'd float through the boundary in silence, unaware that rescue is no longer possible. There would be no sign, no signal, no light to warn you. Only later, as you descended further, would the gravity become violent. The difference in pull between your head and your feet would begin to stretch you, slowly at first, then more and more rapidly. Muscles, organs, bones, everything would be drawn into a thread. This process is called spaghettification, a word almost too soft for something so absolute, and yet even in that, there's beauty. The black hole does not kill out of cruelty. It has no intention, no hunger, no awareness. It is simply a feature of gravity when taken to its extreme. A star dies, its core collapses. Nothing halts the fall. And in its death, something new is born. Not a monster, not a void, but a kind of boundary. A place where the universe says, beyond this, I do not follow, but still we try. We build telescopes to trace the glow of gas swirling at the edge. We map the orbits of stars whipping around an invisible point. We model light bent into circles, photons caught in eternal loops. And finally, in 2019, we captured the silhouette, not the black hole itself, but its shadow. A glowing ring of distorted light, blurred and burning at the edges, wrapped around a darkness we cannot touch. It is an image stitched from radio telescopes spread across the Earth, a planet-sized eye staring into a distant heart of nothing. And the result was not horror. It was awe, quiet, reverent awe, that something so powerful could be so still, that something so heavy could float in the darkness without sound or edge or flame, that the universe could contain a thing so strange and make it feel, somehow, inevitable. Black holes are not holes. They are reminders that even in a universe built on order and light, there are places shaped by silence. That gravity, left unchecked, can fold space like paper and turn time into shadow. That the cosmos is not just what shines, but what draws the shining things inward and holds them without end. And that we are small, yes, but never separate, because every galaxy we see, including our own, orbits quietly around one of these impossibilities. Still, patient, unmoving, the darkest thing in the sky, and the reason the stars stay. All stars die, but not all stars die the same way. For smaller stars, the ending is quiet, almost gentle. Their light fades over time. They shed their outer layers like soft, glowing petals, becoming pale embers known as white dwarfs, slowly cooling in the dark. But when a massive star, 1/12 of times the mass of our sun, nears the end of its life, the finale is anything but gentle. It ends not with a flicker, but with collapse, a sudden, unstoppable inward fall. These stars burn bright and fast. Their cores fuse hydrogen into helium, then helium into heavier elements like carbon, oxygen, silicon, building layer upon layer, like the rings of an onion. At the very center, each layer presses down on the next, heat and pressure climbing to extraordinary levels. The final step is iron, but iron doesn't burn. It doesn't release energy. It consumes it. And so, once iron fills the core, the balance breaks. The star can no longer hold itself up. In less than a second, the core collapses. It doesn't drift or sink. It plunges. At a speed approaching freefall, the heart of the star crushes inward, squeezed by gravity into a state so dense that even atoms themselves are torn apart. Electrons and protons merge into neutrons. The core becomes something like a single atomic nucleus the size of a city. The collapse is not gradual. It is violent, relentless, and irreversible. The laws of physics offer no rescue. Outside the core, the rest of the star, millions of kilometers of gas, suddenly loses its foundation. It rebounds, crashes inward, then erupts outward in a blast so powerful it outshines entire galaxies for a brief, blinding moment. This is a supernova, one of the most energetic events in the universe. It is light and heat and motion exploding into space, and in its wake, what's left behind is something new. If the core was small enough, it becomes a neutron star, a city-sized sphere of ultra-dense matter. But if the original star was truly massive, the core does not stop collapsing. Even neutrons cannot resist. The gravity is too strong. The collapse continues until there is no surface, no form, no resistance left. It becomes a singularity. This singularity isn't a thing in the way we understand things. It is a point, a location where the equations break, where mass is infinite and volume is zero. We don't know if that's true. We don't know what really happens inside. But from the outside, we see only darkness. The event horizon forms, a boundary, a silence. The star, once bright, has fallen inward and vanished. This process is not rare. Somewhere in the universe, a supernova erupts every few seconds. Somewhere, a black hole is born, not as a scar or an absence, but as the product of gravity's most extreme triumph. Collapse is not failure. It's the conclusion of a long, burning story. And what follows is not destruction, but transformation. Some stars die violently, flinging matter in all directions. Their death seeds the cosmos with heavy elements: gold, iron, calcium, the stuff of planets, of bones, of blood. Others die more quietly, sinking into themselves with barely a ripple. But all of them, in their final moments, reveal the delicate balance that held them aloft for so long. They lived by fusion, by pushing outward against gravity's pull. When that engine fails, gravity wins, and gravity always wins. The idea that something could collapse so completely that not even light could escape. This used to sound absurd. For centuries, it was only speculation. Even Einstein doubted such a thing could form in reality. But reality had other plans. We have now observed their shadows. We have felt their ripples in space-time. We have seen the wreckage of stars that could not resist their own weight. In some galaxies, giant black holes form at the center without ever going supernova. We don't yet know how. They may begin as seeds in the early universe, growing by swallowing gas and stars over billions of years. But the more familiar kind, the kind born from stars, reminds us how brief and violent stellar lives can be. Our own sun will never collapse like this. It isn't massive enough. It will puff out gently into a red giant, then shrink into a white dwarf, cooling over trillions of years, peaceful, lonely, cold. But other stars, bigger stars, live harder and die faster. A star 20 times the mass of the sun might burn through its entire life in just 10 million years. And when its time comes, the collapse is swift, brutal, and absolute. We often picture space as cold, still, silent. But the death of a massive star is not quiet. It shakes the fabric of space itself. And what it leaves behind is not a wound, but a presence. A black hole is not an ending. It's a continuation, a new kind of object, where time and space twist into unfamiliar shapes. Even in death, stars do not disappear. They change, they give back, they become part of something deeper. The core that once burned with fusion now curves space so sharply that nothing can climb out. The light that once traveled freely is bent, caught, erased. But that light went somewhere. That collapse had meaning. That star's death will echo through everything it touched, everything it birthed, everything it left behind. Somewhere out there, even now, a star is nearing the end of its fuel. Its core is building iron. Its layers are trembling, and soon gravity will begin its final work. The star will fall inward. The light will rise outward, and the boundary between space and nothing will flicker into being once more. Not a hole, not an absence, a beginning, born in collapse. Time does not behave the same way near a black hole. It bends, stretches, slows down, not metaphorically, not hypothetically, but physically. The deeper you fall into gravity, the more time pulls away from itself. Clocks tick slower. Seconds stretch. A moment becomes an hour, a day, a century, depending on how deep you go. This isn't a trick of the mind or a mathematical illusion. It is a real effect, one predicted by Einstein over a century ago, and now confirmed again and again, not just by equations, but by observation. This idea that time is not constant is one of the most unsettling truths in physics. We grow up thinking of time as fixed, as reliable. It moves forward. It passes evenly. It carries us from birth to death in a straight, steady line. But in the presence of extreme gravity, that line bends. In the grip of a black hole, it breaks. Imagine floating near the edge of a black hole, just outside the event horizon. You're in a protective ship, hovering safely in orbit, close but not too close. From your point of view, everything feels normal. Your heart beats, your thoughts wander, your watch ticks as always. But back home, light years away, time is racing. A minute for you might be an hour there. An hour could be a year. The closer you drift toward the event horizon, the more dramatic the effect. Time for you slows down, not because you feel slower, but because the fabric of space-time itself is stretching around you. If someone were watching you from far away, they wouldn't see you fall. They would see you pause. As you approach the horizon, your image would appear to freeze. Light from you would take longer and longer to escape. Each photon would stretch, redshift, fade. To them, you would appear trapped in slow motion, hovering forever just above the edge. Your fall, from their point of view, would never finish. But you wouldn't notice. To you, the fall would feel natural. You'd cross the horizon without knowing. Your watch wouldn't skip. Your mind wouldn't lag. Inside your own frame of reference, everything would seem ordinary. It's only the universe outside that would begin to fade, racing forward, its clock spinning ahead of yours. This paradox of motion and stillness, of falling and freezing, is one of the most beautiful contradictions in all of science. It's not just theory anymore. We've seen the way time distorts around massive objects. Telescopes have measured stars orbiting the black hole at the center of our galaxy, their light arriving redshifted, stretched by the pull of gravity. Atomic clocks on airplanes, satellites, and mountaintops tick differently depending on altitude, because Earth's gravity warps time just enough to be measured. It's not just black holes. It's everywhere. But black holes take it to an extreme. At the horizon, time appears to stop entirely, not just slow, to stop. From the outside, nothing escapes. Not light, not signals, not time itself. What lies beyond that edge may continue on, may unfold, may stretch and change, but none of it is visible to the universe outside. It's as if the black hole seals off a region of space, turning it inward, keeping its future hidden from view. There are places near black holes where you could, in theory, see the entire future of the universe unfold and fast forward while only moments pass for you. A kind of cosmic time machine, except one you can enter but never return from. In stories, time travel often involves machines or portals or fantastical devices. But in reality, if such a journey exists, it begins with gravity, with motion, with the simple act of falling. This bending of time is called gravitational time dilation, and it's not exclusive to black holes. But nowhere else does it become so vivid. so absolute. Near Earth, the effect is tiny. Near a neutron star, it's more noticeable. But near a black hole, it becomes undeniable. It becomes the difference between years and minutes, between life and death, between a body that ages and a universe that slips ahead without it. And there is no turning back. Once you've crossed the event horizon, your time is no longer connected to the time outside. You exist in a sealed-off future, not destroyed, not erased, but removed. The universe continues. Galaxies drift. Stars are born and die. But you, falling inward, continue along a different path, a slower one, a lonely one. There is something haunting about this, something poetic. That time, which seems so rigid in our lives, so structured and dependable, is actually fluid. It bends in the presence of mass, curls around energy, dances in the presence of gravity, and black holes are gravity's masterpiece. Places where time is pulled so tightly that it frays, breaks, and finally disappears. Einstein didn't just predict this. He described it with elegance, with precision. He saw the shape of the universe not as a static canvas, but as a dynamic fabric, curved and stretched by whatever it holds. His equations told us that mass bends space, and that space tells time how to move. The closer you fall toward a gravitational well, the slower your clock runs. And at the heart of a black hole, time may stop altogether. For decades, these ideas seemed theoretical. Beautiful, yes, but untested. Now, with modern instruments, with space-based observatories and deep radio arrays, we've begun to see these effects play out in the real sky. We've measured the way starlight shifts near the galactic core. We've observed pulsars in binary systems ticking out rhythms that drift with gravity. We've watched the flicker of X-ray light as matter spirals toward the event horizon, slowed by time, stretched by motion. And still, we do not fully understand what lies beyond the edge. Time, it seems, has its own boundary, a place where its meaning changes, where its flow becomes directional, inward, compressed. The edge of a black hole is not just a wall for light, it's a wall for clocks. It divides the universe into two domains, one where moments pass and futures unfold, and one where time itself falls inward, never to return. You are part of this universe. Your body obeys these rules. Your heart beats more slowly on the ground than it does in a plane. Your GPS corrects for time dilation every second. You are already stretched by gravity, already dipped in curved space, but it's subtle, gentle, harmless. The black hole simply takes that familiar bending and carries it to its furthest possible conclusion, a place where time is not lost, but paused, hidden, quiet. And if you were to fall in, you would feel it happen, not all at once, not with a jolt, but slowly, smoothly, inevitably, the way night becomes morning, the way a whisper becomes silence. You would not notice the moment your time left the rest behind, but it would, and it always does. There was a time, not long ago, when black holes were just ideas. Equations scribbled on paper, strange solutions to Einstein's field equations that seemed too wild to be real. They were whispered about, pondered in thought experiments, treated more like paradoxes than possibilities. No one had seen one. No one expected to. They were invisible by nature, after all, things that swallowed light and left behind no reflection. What kind of eye could ever look into a place that gives nothing back? And yet, we did. We saw one, or at least we saw its outline, its echo. The image came in 2019, a ring of fire surrounding a shadow, not a hole, but a silhouette, cast by something that shouldn't be able to cast anything at all. A glowing ring of gas and dust swirling at near light speed, lit not by the black hole, but by the matter dying around it. Light that tried to escape and barely made it. Light bent around the void, orbiting before escaping outward. Twisted, pulled, delayed. What we captured was not the black hole itself, but the way it distorts everything nearby. At the center, darkness. Not because there's nothing there, but because everything is trapped. Light, time, energy. Every particle that crosses the event horizon stays inside, sealed away by gravity so intense that escape becomes impossible. The blackness is not absence, it is confinement. That image, that now famous ring, shows us not what a black hole looks like, but what it does to the space around it. We didn't see the object, we saw the wound, and this vision came not from a single telescope, but from the entire Earth. To see something so small and distant, something 55 million light-years away, we had to turn our planet into a lens, a network of observatories, from the South Pole to Spain, Hawaii to Chile, synchronized to within billionths of a second, all aimed at the same patch of sky. Separately, they captured slivers of data. Together, they formed a planet-sized eye, the Event Horizon Telescope, not one tool, but many. A collaboration of minds and machines across continents, all focused on a single, invisible thing. It was not a simple photograph. There was no shutter, no snapshot. The image was reconstructed from petabytes of raw radio wave data, stitched together by algorithms and models, refined by computation and human intuition. It took years, and when it finally emerged, it was not crisp. It was blurry, soft at the edges, a hazy ring around a perfect void, but it was real. The first direct evidence that the monster at the heart of Galaxy M87 was not just theoretical. That moment, seeing what we were never meant to see, was a turning point. Not just for astronomy, but for imagination. Because we didn't just look at a star or a planet or a distant galaxy. We looked into the edge of space-time itself. We confirmed that these objects, these strange dark engines, aren't just predictions. They're part of the real sky. It's humbling to think about what that image represents. Not just the death of light, but its survival. The photons that reached our detectors had spent thousands, maybe millions of years dancing near the edge of the abyss, trapped in orbits or flung wide by gravity's hand. Many were absorbed, but some escaped, and we caught them, finally, here on Earth, more than 50 million years later. Light that left its home when our ancestors were still climbing trees. Light that survived the pull of a black hole, then crossed half the universe to be seen. It reminds us that even in the deepest dark, some things endure. The shape of the ring confirmed what theory had told us. The size matched the predictions of general relativity. The darkness at the center was just the right width. It was exactly what a black hole should look like, if a black hole could be seen. And in that confirmation, something beautiful happened. The invisible became visible, not fully, not clearly, but enough. Enough to know that the universe is even stranger than we thought, and that our tools are powerful enough to reveal it. But maybe the most astonishing part isn't the black hole at all. Maybe it's what we had to become to see it. A species that turned its entire planet into an eye, that reached across oceans and languages and decades of doubt, just to glimpse something no one thought could be glimpsed. A civilization so curious, so persistent, that it found a way to look into the dark and bring back an image. It wasn't just science. It was vision, and patience, and faith in the idea that the universe, no matter how distant or obscure, can be understood. Not all at once, not completely, but piece by piece, ring by ring, shadow by shadow. That image of M87's black hole is more than proof. It's a portrait of our relationship with the unknown. We stare into what we cannot enter. We trace the edges. We build instruments out of earth and math and silence. And from that silence, we create meaning. The black hole remains, of course, untouched. It doesn't know we saw it. It doesn't care. It continues to spin, to feed, to pull stars apart and consume them. It holds its secrets tight. But now we have seen the shape of its hunger. We have seen its silhouette. We have turned absence into presence, darkness into data. And one day soon, we will see more. the black hole at the center of our own galaxy, others farther still, clearer images, sharper edges, finer detail. But that first glimpse, that soft, glowing ring around a perfect void, will always be the moment the invisible became visible. When we stared into the dark, and the dark stared back. In the quiet heart of every large galaxy, something ancient waits. Not a star, not a planet, not a remnant drifting through space. Something deeper, heavier, invisible, but powerful enough to shape the stars around it. These are the supermassive black holes, colossal creatures, millions to billions of times the mass of our sun, tucked deep into the centers of galaxies like secret engines. They do not roam, they do not flash or shine, but their influence is written into the shape of everything nearby. We used to think black holes were rare, oddities, the tragic end of a few unlucky stars. But as our eyes got better, as our telescopes stretched farther, we began to notice a pattern. The bigger the galaxy, the bigger the black hole at its center. The correlation was too strong to ignore. It didn't matter if the galaxy was a tight spiral or a sprawling elliptical. There it was, every time, a massive gravity well, anchoring it all together. This wasn't coincidence. This was structure, a rule hiding in plain sight. Ours is called Sagittarius A star. It's nestled in the dense core of the Milky Way, behind veils of dust and stars and gas so thick we can't see it with ordinary light. But we've felt its presence for decades. We've watched stars whip around it in tight, violent arcs. Stars the size of our sun, completing full orbits in just a few years, racing along paths that make no sense unless something impossibly heavy sits at the center. Not a cluster, not a hidden mass. One object. 4 million times the mass of the sun, and yet it could fit comfortably inside the orbit of Mercury. Think about that. Something so heavy, so influential, that it can pull entire stars into curved, elliptical dances, and yet it occupies a volume smaller than our solar system's inner core. It doesn't shine, it doesn't pulse, but it's there, unmistakable, watching from the middle of everything, wrapped in silence. And it's not alone. In the center of the galaxy M87, the same one whose black hole was imaged in that first historic ring, lies a black hole more than 6 billion times the mass of the sun. Some go even further, tipping into tens of billions. These are not the children of collapsed stars. They're not born from supernovae. Their origins are older, stranger. Maybe they formed from the collapse of vast clouds in the early universe. Maybe they started small and fed for billions of years. We don't know. But we do know this. Wherever there's a massive galaxy, one of these giants is sitting quietly at the core. And somehow, these black holes and their galaxies seem to grow together. The size of the central black hole is related to the mass of the galaxy's bulge, even though the black hole is only a tiny fraction of the galaxy's total weight. It's as if the two evolved side by side, as if galaxies and black holes weren't separate things at all, but two parts of the same living system, one shaping the other. Some scientists think these giants helped sculpt galaxies in the first place, that the energy they release, when gas and dust spiral into them and heat up, blasts out into space, pushing away matter, slowing star formation, clearing the way for structure. These are not just passive sinks. They may be architects. Their presence may define the very way galaxies mature, grow, and stabilize. In that sense, black holes are not the end of things. They're the shapers, the sculptors, and yet they hide. Even Sagittarius A star, as close as it is in cosmic terms, remains a challenge to see. For most of its life, it stays quiet. It's not consuming much matter right now, but sometimes it flares. It flickers with X-rays and radio waves, brief bursts of energy from particles trapped near the event horizon. It speaks in whispers, in the language of light, bent and broken. We've aimed our telescopes toward it, timing each photon, mapping the dance of nearby stars, collecting faint echoes from the edge of gravity's well. And still, we are only beginning to understand. There's a paradox in all of this. We call them black holes, as if they are voids or absences. But these supermassive ones are anything but empty. They're full of mass, full of gravity, full of history. They sit at the heart of structure, threading galaxies together with their pull. The spiral arms of the Milky Way curve outward from a center anchored by Sagittarius A star, like the arms of a whirlpool stretching from a hidden drain. The more we study them, the more we find that they are not rare, not occasional. They are essential, ubiquitous, maybe even inevitable. And still, they surprise us. Some galaxies have two supermassive black holes, circling each other from a long-ago merger. Others show signs of ancient collisions, shock waves and radio jets that stretch across light years. These are not quiet creatures. When active, they can outshine the galaxy itself, releasing more energy than every star around them combined. We call them quasars. We call them active galactic nuclei. We call them monsters. But they are made of the same physics that holds atoms together, just bigger, stranger, more patient. Perhaps most haunting of all is the scale. These black holes are not confined to some distant corner of the universe. They are everywhere. They are part of the story of galaxies, which means they are part of our story too. The stars that formed the sun, the gas that built the earth, the matter that became your body. All of it lived inside a galaxy shaped by a black hole's gravity. We don't orbit Sagittarius A star directly, not the way our planet orbits the sun, but we exist within its influence. We always have. And so, when you look up at the night sky and see the Milky Way stretching overhead like a river of stars, remember what sits in the middle. Quiet, heavy, patient. It doesn't shine. It doesn't call attention to itself, but it holds everything around it in place. Not just stellar, supermassive. There are times when black holes roar, not with sound, but with light. Brilliant, violent, unstoppable light. In these moments, they become quasars, among the brightest objects in the universe. Not because the black hole itself shines, but because of what happens just outside its edge. Gas and dust, drawn in by gravity, spiral inward, forming a blazing disk that heats up through friction and collision, glowing hotter than stars, hotter than entire galaxies. The matter doesn't fall in quietly. It screams, it blazes. It lights up space from millions or even billions of light years away. Quasars are black holes caught in the act of feeding. These aren't little sips from passing clouds. These are feasts. Chaotic, radiant devourings that release more energy than every star in the host galaxy combined. A single quasar can outshine trillions of suns. They send jets of radiation across the cosmos, carving through intergalactic space, disrupting the growth of nearby galaxies. They are not just bright. They are disruptive, active, alive, in their own way. And yet, this brightness isn't permanent. Feeding is a phase, not a state. Black holes don't always consume. Most of the time they are silent, still, not empty, but unfed. Like a sleeping volcano, they hold their power close, invisible, until something stirs them awake. A passing star, a cloud of gas, a galaxy drifting too near. Then the quiet ends, the spiral begins. The black hole starts to feed again, and the light returns. This duality between silence and fury is one of the most haunting things about black holes. The same object that hides completely when left alone can suddenly become the beacon of an entire sky. It doesn't change. It doesn't grow limbs or change shape. It just eats, and in eating, it glows. But that glow is not from the black hole itself. Nothing escapes the event horizon. No light, no signal. What we see is the destruction that happens just outside that final edge. The glowing accretion disk, the jets of plasma accelerated to near light speed, the tidal shredding of stars into glowing ribbons. It's a kind of violence we can only observe from a safe, cold distance. It's beautiful, terrifying, almost sacred. And then, just as suddenly, it stops. The fuel runs out. The cloud is consumed. The feeding ends. The light fades. What was once the brightest thing in the universe becomes invisible again. Not because it's gone, but because it no longer has anything to show. The black hole hasn't moved. It hasn't died. It's simply waiting again, motionless, quiet, patient beyond imagination. Most black holes we know of are in this quiet phase. Sagittarius A star, the supermassive black hole at the center of our own galaxy, is one of them. It flares occasionally, releasing brief pulses of X-rays and infrared light as tiny bits of matter fall in. But mostly, it does nothing. It sits. It waits. It exerts its pull without display. In a universe where brightness often means life and activity, this kind of quiet is unsettling, but it's real. Most of the time, black holes are not destroyers. They're just there, and the contrast is startling. To think that the same object, utterly dark and motionless, can become a cosmic lighthouse if given the right meal. That feeding transforms them into quasars, radio galaxies, active nuclei that shape the structure of the cosmos. And when they're full, when they've fed enough or run out of fuel, they disappear again into silence, not smaller, not weaker, just hidden. This rhythm, feast, and silence is part of the life cycle of galaxies. When black holes feed, they can shut down star formation, blowing away the gas that would otherwise become new suns. They regulate growth, they control pace, and then they rest. The galaxy catches its breath. The stars form again, until the cycle starts over, and all of it depends on chance, on proximity, on collisions and clouds and cosmic tides. A black hole doesn't go out searching. It doesn't move toward prey. It waits. It lets the universe come to it. And when the moment arrives, when a star drifts too close or a gas cloud tumbles inward, it opens its mouth. Not with teeth, not with hunger, but with gravity. That gravity doesn't just pull, it tears. Matter near a feeding black hole doesn't fall like rain. It spirals. It shears into ribbons, heats to millions of degrees, and radiates across the spectrum. We see it in X-rays, in ultraviolet, in gamma rays. We hear it in the hum of radio waves echoing through space, and all of it, the chaos, the light, the noise, comes from matter dying just outside the edge. No one knows how long these feeding frenzies last. Some may flare for thousands of years, others for millions. But eventually, the banquet ends, and the black hole, now full, returns to quiet. Still there, still heavy, but invisible once more. In this way, black holes are not just objects. They're phases, states of being, sometimes quiet, sometimes blinding, sometimes sleeping for eons before stirring awake for just a heartbeat of cosmic time. We see them when they allow us to, when the conditions are right, when the universe hands them something to eat. And there's something deeply humbling in that these forces, so extreme, so massive, can flicker in and out of visibility, depending only on whether there's fuel nearby. They do not announce themselves. They do not demand attention. They simply wait, patiently, eternally. The universe is full of things like this, powerful, silent forces that shape the visible world from just behind the curtain. We live in the light, but we are surrounded by shadow, and sometimes, just for a moment, the shadow glows, then it goes quiet again. Not gone, just waiting. Gravity, in most places, is subtle. It's the slow pull of your body to the earth, the curve of a planet around its star, the quiet order behind the orbits we take for granted. We move through it daily, barely noticing. It is dependable, predictable, familiar. But near a black hole, gravity forgets how to whisper. It becomes strange. It becomes absolute. And it begins to affect even the things that are meant to be untouchable. Things like light. There is a place near a black hole where gravity becomes so intense that even photons, which normally travel in straight lines through the vacuum of space, are forced into something altogether different, not just bent, but caught. At a very specific distance from the black hole's center, light can orbit. Not for a moment, not as a brief curve before escaping again, but endlessly, trapped in a circle, forever falling but never crossing the edge. This place is called the photon sphere. It sounds like science fiction. Light, the fastest thing in the universe, caught in a loop. But this isn't theory for its own sake. This is geometry. When space itself bends hard enough, the shortest path between 2 points no longer looks straight. It bends, folds, loops. Light always follows the straightest possible path. But in curved space, the straightest path may circle back on itself. So the photon, doing what it always does, finds itself in orbit. This isn't a comfortable orbit, like a planet tracing a slow ellipse. It's a tight, unstable loop, a razor's edge of balance. Any disturbance, an interaction with matter, a slight nudge, will send the photon inward toward doom or outward into freedom. But in principle, if left perfectly alone, it could remain there. A ring of light, endlessly circling, like a halo made of trapped time. This is the photon sphere. It marks a transition. Outside of it, light can still escape the black hole's pull, though often with difficulty, bending and warping around it in strange arcs. This bending is what allows gravitational lensing, the cosmic mirage that lets us see light from objects behind the black hole, distorted but visible, wrapped into glowing rings. But once you pass the photon sphere, escape becomes less likely. Things are falling faster. Space itself is curving more steeply. And eventually, inevitably, there comes a point where escape is impossible. That point is the event horizon. Between the photon sphere and the event horizon, light still exists, but it has no path outward. It moves inward with every tick of time. Every photon in this region is doomed to cross the horizon, to fall into the singularity. There are no stable orbits here, no hesitation, just a smooth, unstoppable slide into black. But it's that region, just outside, the photon sphere, that shows us how radical gravity becomes. Not just because of what it does to objects, but because of what it does to space itself. We tend to think of space as a container, an empty stage upon which matter and energy dance. But near a black hole, that illusion breaks. Space is not passive. It is shaped, warped, dynamic. And where that curvature is strongest, the rules we're used to begin to bend with it. When Einstein formulated general relativity, he didn't describe gravity as a force. He described it as the curvature of space-time. Mass tells space how to curve. Space tells matter how to move. And light. Light obeys space. Always. It doesn't resist. It doesn't correct. It simply follows the shape of the universe, even when that shape folds into itself. That's why we can see rings around black holes, not from the black hole itself, which emits nothing, but from the way it bends the light of everything around it, photons that were never meant for us. Light from distant stars or glowing gas are curved toward our eyes by the gravity of the hole. In some cases, the light circles the black hole once, twice, even 3 times before it escapes toward Earth. Each orbit adds distortion, delay, layers of time wrapped around gravity. And in this way, black holes allow us to see what would otherwise be hidden. Not directly, not clearly, but through echoes, through curves, through light that's been bent almost into submission, then released. It's a kind of gravitational art. Images drawn not by the light itself, but by the shape of the space it passed through. The photon sphere is not a surface. You couldn't stand on it or point to it. It's a threshold, defined not by matter, but by math. A place where the equations governing light and motion intersect in perfect, uneasy balance. A place that's always just out of reach, because any attempt to stay there would end in falling or flying away. It's not a place you can visit. It's a place that exists only in motion, but it's real, and knowing it's real changes the way we think about what's possible. Because if gravity can bend light into loops, if it can sculpt the paths of photons into rings and spirals, then nothing in the universe is quite as linear as we thought. There are no truly straight lines, only paths shaped by invisible curves, slow turns that we don't always feel, but that define everything we do. In the deep cosmos, the light we see may have taken a journey we can barely imagine. It may have circled black holes, skirted photon spheres, dipped toward event horizons before turning back. And when it finally reaches us, a bent, delayed, stretched, we capture it with our telescopes and call it observation. But in truth, it is memory, the memory of a path taken through curved space. So the next time you look up at the stars, know that not all light moves freely. Some of it is still trapped, still circling, still dancing near the edge of gravity's deepest well, not yet fallen, not yet escaped. A ring of photons orbiting forever, where space curves so sharply that light itself can't find a way out. And that ring, silent, invisible, eternal, is one of the strangest, most beautiful things the universe has ever allowed. There's a calm sort of terror in imagining what would happen if you fell into a black hole. Not because of the darkness, or even the finality of it, but because of what happens to your body on the way down. Hollywood often shows it as sudden. One moment you're floating, the next you vanish. But the truth is more elegant and far stranger. The descent is quiet, smooth, deceptively gentle at first, but with each passing moment, the laws of gravity begin to assert themselves in ways that no human body can withstand. This isn't just falling. This is falling with a difference. Near any massive object, gravity is stronger the closer you get. That's how tides work on Earth. The moon pulls more strongly on the side of Earth facing it than the far side, stretching our oceans into bulges. But around a black hole, this difference, this gradient in gravity, becomes extreme, unthinkable, catastrophic. Imagine approaching feet first. At some point, the pull on your legs becomes significantly stronger than the pull on your head. The lower half of your body begins to accelerate faster than the upper half. It's not that you're being yanked. It's that you are falling unevenly, in pieces. Your body begins to stretch. The molecules at your feet are accelerating more than the ones at your chest. The result is a long, slow tearing, not from the outside in, but from within. Your atoms are no longer falling together. They are separating. This is not a hypothetical. It's a well-understood process, a precise, inevitable outcome of intense tidal forces. And it has a name both absurd and fitting: spaghettification. You become a thread, not metaphorically, but literally. Your body narrows as it lengthens. You stretch thinner than a strand of hair, then thinner than a red blood cell, then thinner than the wavelength of visible light. There is no limit to the elongation except the laws of physics themselves. And at some point, your structure, your cohesion, your identity disappears. There's no pain, not the way we usually understand it. Pain requires nerves. Nerves require a functioning body, a processing brain. Long before the extremes of spaghettification set in, your brain would be unable to interpret signals, unable to form thought. Time for you would lose meaning. Perspective would collapse inward, just like space. But from the outside, from the distant view of someone watching your fall, everything would seem frozen. You would slow as you approached the event horizon. Your image would stretch and fade, warped by light, smeared into a redder and redder smear until you vanished entirely. A ghost trailing toward the edge, never quite touching it. This is the cruel beauty of relativity. From your point of view, you fall smoothly inward. Nothing marks the crossing of the horizon. No flash, no warning. Just a continued descent into increasing gravity, increasing time dilation, increasing curvature. But from the outside, you never quite arrive. You become a story without an ending, a signal stretched infinitely thin. This dual view, one from the inside, one from the outside, is part of what makes black holes so strange. Physics doesn't break, but it does fork. Your experience and the universe's experience become two different narratives, both technically correct, neither complete. And in both versions, the stretching is real. It's not only humans that suffer this fate. Any object that comes too close, comets, stars, clouds of gas, meets the same outcome. They are stretched into tendrils, spirals of matter pulled apart by gravity itself. The process feeds the black hole. But it also paints the sky. Infalling matter heats as it stretches, glowing in X-rays and ultraviolet, lighting up the space just outside the edge. In a way, spaghettification makes black holes visible. Their destruction is what lets us know they're there. For smaller black holes, this effect happens quickly. You'd be torn apart long before you ever reach the event horizon. But for supermassive black holes, the difference in gravitational pull over a human body is much gentler, at least at first. You might cross the event horizon completely intact, unaware that anything has changed, only to be shredded moments later when the tidal forces finally catch up. Either way, the outcome is the same. There's something profoundly humbling in knowing that the universe contains objects so powerful, so precise in their violence, that even the shape of your body is no match. That even light can be stretched, redshifted into invisibility. That matter, under the influence of gravity alone, can be turned into a thread thinner than a beam of starlight. And still, black holes are not villains. They don't hunt. They don't consume out of malice. They simply are. They obey the rules written into the fabric of space-time. Spaghettification is not punishment. It's math. A silent equation playing out over and over, across billions of years, on whatever dares to get too close. So when you hear the word, when you laugh at its oddity, its whimsy, remember what it stands for. It's the name we gave to one of the most extreme transitions matter can experience. From structured to scattered, from whole to undone. It's a line crossed not in fire, but in gravity. A slow unmaking, invisible, except in theory, unstoppable once it begins. And it is happening, somewhere, right now. A star torn apart, a planet pulled into ribbons, a molecule unraveling at the edge of space, all stretched thin, past the limits of recognition, past the point of return, downward, forever, into the deep. In the emptiness of space, silence is not just expected, it's a law. Sound, as we know it, needs something to travel through. It needs air, water, a medium that can carry vibration from one molecule to another. And in the vacuum between stars, there is none of that. There is only void. For a long time, that meant black holes, for all their drama, for all their power, were utterly silent. Their influence could be seen, their presence could be inferred, but they couldn't be heard until they were. In 2022, something shifted in the way we think about silence. NASA released a sound, a real one. Not a metaphor or a simulation, not the typical data sonifications often turned into music for educational effect. This was something different. This was the voice of a black hole. Or, more precisely, the sound created by a black hole's influence on its environment. It came from the Perseus galaxy cluster, over 240 million light-years away. A place filled not with air, but with a thin soup of hot intergalactic gas, just enough material to carry a whisper. And in that whisper, a pressure wave. The black hole at the center of Perseus had sent out ripples, not light, not matter, but sound waves, pressure pulses moving through the gas, ringing outward like the toll of a cosmic bell. These weren't sudden booms or explosions. They were slow, deep vibrations, waves on scales of hundreds of thousands of years, rippling across distances we can't properly picture. The frequency was far below what the human ear can hear, millions of times deeper than the lowest bass note we can perceive. But it was real, and we heard it. Scientists raised the pitch, compressing the scale of time and space, translating the unhearable into something within the range of our ears. What emerged was a moaning, ghostly hum, a sound that felt less like a note and more like the echo of a thought. It didn't resemble music. It resembled the memory of music, as if the universe itself had exhaled, and we, impossibly, had caught the sigh. The sound was not from the black hole itself. Nothing escapes the event horizon. Not light, not energy, not vibration. But just outside, in the region of influence, the black hole had stirred the gas. That motion, that pulse, was enough to make the invisible visible, audible, tangible, in a way we never imagined. What we heard wasn't the black hole screaming, but the space around it resonating, like a drum stretched across nothingness. It's easy to forget how much motion there is in silence. Just because we can't hear it doesn't mean it's still. Space is full of waves, gravitational, electromagnetic, pressure-based. These waves roll endlessly through the cosmos, rippling through gas clouds, starlight, dark matter. And now we know they can ripple through us too, in sound. There's a strange intimacy in hearing something that old. The waves captured from Perseus began their journey long before humans walked upright, before Earth had continents in their current places, before mammals, before flowers. These waves traveled for hundreds of millions of years, carrying with them the echo of a black hole's breath, a ghost of motion so deep and slow it might have passed through galaxies unnoticed. But not through us. Not anymore. We've always imagined the universe as a kind of visual spectacle. Stars to gaze at, nebulae to photograph, light years to map and measure. But now we know it can hum too. It can sing, if you know how to listen. That hum is not random. It's structured. It carries information. It tells us about the mass of the black hole, the temperature of the surrounding gas, the density of the cluster. It is science, yes, but it is also music. A kind of music no instrument could ever play. And maybe that's what makes it so unsettling, because it doesn't follow any rhythm we understand. It doesn't build toward a chorus. It doesn't end. It just goes on. A droning, patient vibration from a body too massive to care if we listen, too ancient to care if we understand. But we do listen, and for a moment, we feel smaller than ever, and somehow more connected. Because if a black hole can stir sound into being, then silence is no longer empty. That sound reminds us that the universe is not a painting. It is not a still image to be framed and admired. It is alive with motion, with turbulence, with waves that take centuries to cross a room that no one is in. The black hole doesn't announce itself with flashing lights or thunderclaps. It pulses, slowly, deeply, continuously. And in those pulses, something stirs the medium around it just enough for the silence to become a voice. And maybe we've always needed that. Not a roar or a bang, but something quieter, something ancient, something that tells us the universe isn't just expanding, it's resonating, not loudly, not for long, but enough. Enough to remind us that even the deepest dark can speak. That void is never truly void, and that sometimes, across impossible distances and through unimaginable time, the universe calls back. Even if what it says is only a low, endless hum, even if what we hear is just the breath of gravity itself, it begins with a question older than science itself. What if there was a way to travel, not across space, but through it. Not by moving forward, inch by inch, but by folding the map entirely, taking two distant points in the universe and letting them touch. A bridge, a tunnel, a doorway cut through the fabric of reality itself. That idea, strange as it sounds, has a name: wormhole. And black holes, for all their destructive power, may be hiding something even stranger inside them. In the equations of general relativity, the math that governs gravity and space-time, wormholes are possible. They are allowed, not common, not easy, not stable, but not forbidden. They appear as solutions to Einstein's field equations, just like black holes do. But instead of being one-way chasms that crush everything into singularities, wormholes offer another outcome: a tunnel, a path, a passage from here to elsewhere. This elsewhere could be anywhere: another point in space, another time, another universe. The connection between black holes and wormholes begins with their geometry. A black hole curves space inward, endlessly, until space becomes so bent it folds in on itself. But what if that curve didn't end in a singularity? What if instead it turned back outward? What if the black hole was one mouth of a tunnel, and on the other end was another mouth? Another black hole, or perhaps something else entirely? That's the structure of a theoretical wormhole: two ends, joined by a throat of warped space, existing not as fiction, but as mathematics that nearly works. Nearly. The problem is stability. In the models, wormholes collapse almost instantly. They pinch off before anything can pass through. To hold one open, you would need something exotic, a kind of matter that repels gravity rather than succumbing to it, what physicists call negative energy density. We've never seen this kind of matter in nature, but strangely, we've also never ruled it out. Quantum mechanics allows for fleeting instances of negative energy, tiny fluctuations that pop into and out of existence in the vacuum of space. It's not enough to build a wormhole, but it hints that the ingredients might exist, if only briefly. So the idea survives. Some theories go further. They suggest that certain black holes might already be wormholes, hidden in plain sight, that falling into the right kind of black hole, one with the right spin, the right charge, the right structure, could lead not to destruction, but to somewhere else. That behind the veil of the event horizon, the universe may have folded in ways we cannot yet trace, and that what we call singularities might be mouths to other worlds. It's not entirely science fiction, it's just science with a question mark. Still, even if wormholes exist, travel through them might be impossible. The forces involved could shred any matter long before it reaches the throat, or the exit might not lead anywhere habitable, or it might lead nowhere at all. An endpoint with no space, no time, just stillness. A trap, disguised as a door. And yet we keep wondering, because if wormholes could be created or stabilized, the implications would be staggering. Light years would become minutes. Galaxies could be neighbors. Messages could outrun beams of light. The structure of the cosmos itself would have shortcuts. Not because we broke the speed limit of the universe, but because we redefined the road. In fiction, wormholes are neat, elegant things. Portals that open like flowers, symmetrical and predictable. But in reality, they would be chaotic, jagged, unstable, and beautiful. They would bend not just space, but perception. You might look into one and see your destination distorted, as though through water. You might hear echoes of your own voice arriving before you speak. You might witness time itself unwind, and yet they remain, for now, unproven. We have no evidence, no signal, no structure in the sky that tells us a wormhole is waiting. But the equations haven't gone away. The possibility lingers, not because we need it to be true, but because the math hasn't stopped whispering. And sometimes, the universe follows its equations more faithfully than it follows our imaginations. That's the space wormholes live in. Not fantasy, but not yet fact. a liminal place between certainty and speculation, between what we can observe and what we can only hope to test. We may never find one, or we may find they're all around us, hidden in gravitational wells, masked as black holes, invisible until the right lens is applied. What we do know is that black holes already distort space and time, already warp light and twist causality. If any place in the universe is strange enough to hold a doorway to somewhere else, it would be there, in the places where gravity rules absolutely and the normal rules no longer apply. It might be silent, or it might hum, or it might stretch us thin like spaghetti before we could ever see what's on the other side. But the possibility remains, delicate and dangerous. A tunnel, a trap, a shortcut, a dream, and maybe one day, a way through. For something so powerful, so devouring, so seemingly eternal, the idea that a black hole could one day vanish feels almost like heresy. And yet, nestled within the equations of quantum physics, there is a whisper. A strange, quiet process that contradicts everything we once thought a black hole was. Not a prison from which nothing escapes, but a leaky container, losing energy particle by particle, moment by moment, in a kind of cosmic exhalation. This is Hawking radiation, and it means black holes can die. Not violently, not with explosions or collapse, but slowly, imperceptibly, like steam drifting from a cup left out in winter air. It begins at the edge, at the event horizon, the point of no return, the place where gravity becomes so absolute that even light cannot climb free. Quantum theory tells us that even in the vacuum of space, particles are never truly still. Pairs of particles and antiparticles constantly bubble into existence, borrowing energy from nothing, lasting for a flicker of time before annihilating each other. This strange temporary dance happens everywhere, even at the edge of a black hole, and sometimes one of those particles falls in. When that happens, its partner escapes. It becomes real. It leaves the horizon, carrying energy with it, and flies off into the universe. That escaping particle is Hawking radiation, and the energy it carries must come from somewhere, from the black hole itself. Every escaping particle takes with it a tiny fraction of the black hole's mass, not enough to notice, not enough to measure with current tools. But over time, over spans of years so vast they make galaxies seem young, that slow leakage builds. The black hole begins to shrink. Its horizon contracts. Its temperature rises, slightly, and the process accelerates. This isn't fast. It isn't dramatic. For a black hole the size of a star, the time it would take to fully evaporate is beyond comprehension. Many orders of magnitude longer than the current age of the universe. But the numbers don't lie. The equations, for all their coldness, speak of an ending. The most powerful objects in the cosmos are not immortal. The idea came from Stephen Hawking in 1974 when he blended quantum theory with the curvature of space. He didn't expect to find it, but there it was, folded in the math like a hidden message. It changed everything. Before that, black holes were thought to last forever, swallowing information, mass, and energy, never giving anything back. But now, they seemed fragile, temporary, able to die not with a bang, but a long, drawn-out sigh. This also raised another question. What happens to everything the black hole once held? If it evaporates completely, where does the information go? Does it vanish with the event horizon, or is it somehow encoded in the radiation that escapes? This is the infamous information paradox, a mystery still unresolved. Because in quantum mechanics, information isn't supposed to be lost, but a black hole seems to erase it. If it fades entirely, then what becomes of everything that once fell inside? All the light, the matter, the structure. Does it leave an echo, a scar, or nothing at all? Maybe, in its final moments, a black hole flares. Maybe the evaporation accelerates until the last pieces unravel in a sudden release of light and heat. Maybe it simply winks out. No sound, no trace, no goodbye. Maybe the laws we think we understand begin to blur at the very end. There is no way to know for certain. Not yet. What we do know is that black holes grow cold before they vanish. They lose their power quietly, like embers buried in ash. At their peak, they're among the brightest things in the universe when feeding. But at the end, they're dark again, cold again, not because they are swallowing light, but because they are no longer strong enough to keep it. They radiate their last warmth into a cosmos that no longer notices. They return what they took, one particle at a time. There's a strange poetry to that. The most feared objects in the universe, the monsters of gravity, turn out to be temporary, not defeated, not broken, just completed. Like a star burning out, like a wave sinking back into the sea. Not everything ends in violence. Some things simply fade, and this fading tells us something important, that even the strongest structures are subject to time, that permanence is an illusion, that scale doesn't protect you from entropy. A black hole doesn't escape the laws of thermodynamics. It bows to them, slowly, reluctantly, but inevitably. One day, in a future so far off we can barely name the numbers, when the stars have all burned out and galaxies are cold dust, black holes may be the last luminous things left, still evaporating, still breathing, still giving off their soft, invisible glow. Not enough to light the dark, but enough to remind us that even in silence, change continues. And then, eventually, they will be gone. Not with a roar, but with nothing. No boundary, no horizon, no core. Just the memory of mass, returned to the fabric of space. Just the echo of something that once was eternal, now gone. Out there, in the vast quiet, two invisible giants can begin a slow, spiraling dance. For millions of years they orbit each other, circling in a mutual grip. Black hole locked to black hole, moving with a grace that belies the chaos to come. They don't glow, they don't shine. To most of the universe, they are silent, unseen, and lost within the folds of space. But their pull is real. Their gravity is immense, and with every orbit, they inch closer. What begins as a distant waltz becomes a gravitational embrace. The space between them shrinks. The energy of their motion bleeds into the universe in the form of ripples. Gravitational waves that spread outward at the speed of light. Not light waves, not sound. These waves are deeper. They are distortions in the fabric of space itself, stretching and compressing everything they pass through, though so subtly that it takes an instrument of exquisite sensitivity just to notice them. For a long time, we couldn't. The theory said they should exist. Einstein predicted them more than a century ago. But for decades, they remained undetected, elusive phantoms in the noise of the cosmos. Then, in 2015, the silence broke. Two black holes, billions of light years away, spiraled into one another in a final, catastrophic collision. The mass of three suns was converted into pure energy and radiated outward in a burst of gravitational waves, and we heard it. LIGO, an observatory designed to feel the smallest of tremors in space-time, recorded the signal. A chirp, lasting just a fraction of a second, but unmistakable. A sound not of air, but of the universe itself, ringing like a bell. We had felt space shudder, and in that moment, black holes became louder, more real, more intimate. They were no longer theoretical traps waiting in distant corners of the galaxy. They were actors, dancers, partners in an ancient cosmic choreography we had only just learned how to listen to, and they had stories to tell. Since then, we've heard dozens more, each one different. Some are massive, others smaller. Some come from ancient collisions, others more recent. But all of them carry a signature. a ripple that begins in the slow spin of orbit and ends in a sudden union. In that final moment, the two horizons merge into one. The result is a larger black hole, briefly distorted, vibrating with the shock of its new shape, like a drumhead after a strike. Then it settles, silent once more, its past absorbed, its future rewritten. These mergers are not rare. Across the universe, wherever stars are born and die, wherever galaxies pass close enough to interact, black holes can find each other. Gravity does the rest. They spiral, collide, and become something new. Sometimes they merge quietly, hidden behind veils of dust and light. Sometimes they roar, sending out waves strong enough to cross the universe. Always, they change the shape of space. Always, they leave a mark. It's humbling to think about. That even now, as you lie still and quiet, space around you may be shifting ever so slightly from the distant echo of two black holes colliding long before Earth even formed. The wave passes through everything. Through you, through time, through matter. Unstoppable, but so faint you wouldn't notice, unless you're listening in just the right way. We are listening now, and what we're hearing is extraordinary, because gravitational waves don't just confirm the existence of black holes. They let us measure them. We can weigh them by the shape of the signal. We can estimate their distance. We can even begin to guess how they formed. Were they born from massive stars in the same system? Did they drift together across light years, pulled by the quiet hunger of gravity? Or were they remnants of earlier collisions, part of a chain reaction of cosmic mergers echoing through deep time? We're only just beginning to ask, and the implications ripple outward, just like the waves. They could help us map the history of the universe, trace the growth of galaxies, test the limits of Einstein's theories, maybe even glimpse new physics hidden in the noise. With every detection, we get a little closer to seeing black holes not just as endpoints, but as events, processes that shape the very geometry of the cosmos. Because a merger isn't just the end of two black holes, it's the creation of one new one, a transfer of identity, a recombination of gravity. And though we cannot see it with our eyes, though the collision releases no light, the energy unleashed is vast. For a brief moment, it can outshine the entire visible universe in gravitational power alone. All of it silent, all of it in the language of space and time. When black holes merge, they don't just swallow stars. They teach us something profound, that even in the darkest places, even in silence and invisibility, there is motion, there is interaction, there is change. The universe isn't static. It's alive with tension and resolution, with unions and departures, with the ongoing pulse of gravity stitching everything together. And so, from the depths of silence, we learn to listen, not with ears, but with understanding, with instruments built to feel the tiniest tremor in reality, with questions whispered across space, because somewhere, right now, two black holes are drawing near, and the universe is waiting to ring again. Most people imagine black holes as still things, unmoving and ancient, like statues carved from the very night. But the truth is far stranger. A black hole can spin, not just turn gently or drift with a lazy rotation, but whirl at speeds that defy the imagination, close to the speed of light itself. This is no slow cosmic pirouette. It's a storm of gravity so intense, it pulls on the very fabric of space around it and twists it into motion. This effect has a name, frame dragging, and it means exactly what it sounds like. The black hole doesn't just exist in space, it takes space with it. It spins not just matter, not just light, but reality itself. Imagine the surface of a still pond, flat and calm. Now picture a marble dropped into it, not just sinking, but spinning furiously as it falls, pulling the surface water into a whirlpool. Now replace the pond with space-time and the marble with something millions of times the mass of the sun, and you begin to glimpse the scale of what's happening. Around a spinning black hole, directions begin to blur. There is no fixed up or down. If you orbit in the same direction as the spin, you can get closer to the event horizon without being pulled in. If you try to orbit against it, the black hole resists you. It's as if the entire structure of space around it has become a river with a current, and the current always flows in the direction of the spin. Even light feels the difference. Its path curves more dramatically. Its escape becomes more difficult. The shape of the black hole's influence stretches outward, wider and stranger than in a static version. There's a region outside the event horizon called the ergosphere. In this boundary zone, nothing can remain still. Not because of gravity pulling inward, but because of space itself rotating. You could hover outside a non-spinning black hole with the right force counteracting the pull. But here, in the presence of spin, that's no longer possible. To remain fixed is to defy the rotation of space-time itself, and that's not something matter can do. So everything moves, everything swirls, the rules bend, and that bending has consequences. The spin of a black hole affects how it eats, how it grows, and how it changes the behavior of light, jets, and matter around it. It can accelerate particles, shape magnetic fields, even twist entire accretion disks into strange, warped spirals. Some scientists believe it's this rotation that powers the bright beams shooting from the poles of certain black holes, jets that span thousands of light years and light up galaxies like cosmic lighthouses. The energy for those might come, at least in part, from spin, from the relentless whirl of a singularity wrapped in shadow. We've even measured it. Not directly. Nothing with black holes is truly direct, but through inference, through the patterns of X-ray emissions, through the shape of surrounding gas, through the subtle fingerprints that rotation leaves on the light it fails to trap. And what we've seen is staggering. Some black holes spin so fast that if they went any faster, they would violate the equations that allow them to exist. They approach the limit, the edge of possibility. A black hole spinning at near light speed is about as extreme as anything in the universe can be without tearing itself apart. But it doesn't tear, it just keeps spinning, and that spin is ancient. Born in the collapse of a star that once had its own rotation, its own momentum. When the core of a dying star collapses into a black hole, the law of angular momentum says the spin has to go somewhere. And since the collapsing object is shrinking to a fraction of its original size, its spin must increase. Like a figure skater pulling in their arms, tightening their radius, the rotation accelerates. But instead of a skater, we have something with the mass of suns, compacted into a sphere smaller than a city. The result is something monstrous, elegant, and wildly fast. Over time, black holes can gain or lose spin. Merging with other black holes can change their rotation, sometimes speeding it up, sometimes slowing it down, depending on the angle of the incoming partner. Matter falling in can also influence spin, especially if the infall has a preferred direction. A steady diet of matter from a swirling disk will, over eons, align a black hole's rotation with the disk's motion, like a gyroscope locking into the rhythm of a surrounding system. But once spin is established, it becomes a kind of signature, a defining feature. A spinning black hole doesn't just bend the rules of movement, it bends time. Clocks near its edge tick slower. Trajectories curve in spirals instead of arcs. Escape becomes more complicated, more conditional. Even the shape of the event horizon itself changes. Instead of a perfect sphere, it flattens slightly at the poles and bulges at the equator, like a planet spun too fast for its own symmetry. And yet, for all that, it's still invisible. Still a shadow on space. Still defined not by its form, but by its effects. You'll never see the spin. You'll only feel it, if you're close enough, in the way space stretches beneath you, and time slips around you, and the stars beyond begin to bend in strange, impossible patterns. The deeper truth is this: a spinning black hole is not just a collapsed object. It's a machine for twisting reality. A vortex made of mass, motion, and time. Not just a sinkhole in space, but a dynamo of curvature and consequence. A place where the universe is no longer passive but dynamic, changing with every revolution. And the more you understand it, the stranger it becomes. Because the closer something spins to the edge of light speed, the more time distorts, the more energy concentrates, and the more the very idea of stillness becomes irrelevant. In that final blur, where mass, space, and momentum blend into a single motion, a spinning black hole becomes something else entirely. Not just fast, but fundamental. In the gentle darkness that cradles our galaxy, there may be millions of black holes drifting through space, unlit, unmarked, and almost entirely unnoticed. Not the supermassive kind that anchors a galaxy. Not the rare ones caught mid-meal, glowing as they tear matter apart. These are quieter, smaller, born in the depths of stars, and now slipping silently through the spiral arms of the Milky Way like forgotten echoes of ancient fire. They are stellar mass black holes, and they are everywhere. Each one no bigger than a city, yet holding the mass of several suns, not shining, not flaring, not even whispering, just moving, slowly, steadily, through the galactic haze, pulling slightly on the stars around them, bending the path of light, shifting the dance of the visible world with their invisible gravity. And because they emit no light, we don't see them, not with telescopes, not with the naked eye. We infer their presence by what they touch, like the way you'd notice a breeze only because the curtain sways, or the way you'd know someone passed by because the floorboards creaked in their wake. They leave traces, but never a trail. Most of them will never be known. Right now, one could be moving silently through an unremarkable patch of space, just beyond the arc of a star you've never heard of. It might be alone, or maybe not. Some black holes might still cling to a companion star, the leftover partner of the star that collapsed. These binary systems can sometimes betray themselves, not through light, but motion. The visible star wobbling in a tight, curious orbit, like it's being tugged by a ghost. We can measure that wobble, and sometimes we find what's causing it. But most are loners, wandering remnants. They don't hunt, they don't search. They drift on paths shaped by ancient forces, guided by gravity alone. And because they're dark, we have no easy way to track them. We rely on moments of chance. A black hole passing in front of a distant star just so. Its gravity bending the light like a lens, making that star briefly flare brighter. These events are rare, but we've seen them. Glimpses of something that doesn't glow, revealed only by the way it warps the light behind it. And those glimpses hint at a deeper truth. There could be 10 million stellar mass black holes in the Milky Way, or more. A population of shadows drifting in the spaces between stars, hidden in the folds of spiral arms, in the dusty lanes that wind between constellations. They don't follow us, but they surround us. And because our solar system moves too, tracing a slow orbit around the galactic center, it's entirely possible we've passed near one, perhaps a few light years away, perhaps closer, and we didn't know. No light bent dramatically toward us, no star flickered or flared, no motion gave it away. The black hole passed, indifferent and unseen, a silent knot of gravity in the cosmic sea. There is something both terrifying and beautiful about that the universe can be filled with things so powerful, so final, and yet so utterly quiet, that a force capable of tearing a star apart can slip past undetected, like a shadow crossing a room without sound. These black holes are not malicious. They don't chase. They don't consume everything in sight. They simply are. And most of the time, that's all they need to be. Their gravity is enough to bend the rules of light and space, to reshape the orbits of stars, to stretch time at their edges, but not enough to announce themselves loudly. They remain background players in a galactic drama we're only beginning to understand. Sometimes, we wonder if a black hole has ever come close enough to truly affect us. not to devour Earth, not even remotely, but to pull subtly on the solar system, to shift the Oort cloud that surrounds us, to fling comets inward that otherwise would have stayed in the cold. These are theories, not certainties, speculations whispered by astronomers trying to piece together the long-term history of our planet's dance through space. But they're not impossible. With so many black holes wandering unseen, it would be strange if none had ever brushed near us, and stranger still if one never will again. They are not ghosts, but they act like them, not in the way they haunt us, but in the way they remain just out of sight, just beyond perception. Always there, always real, but only visible through the disturbances they cause, the gravitational fingerprints they leave behind. Their existence reminds us that much of the universe is not what we see, but what we miss. And so we watch. We build instruments sensitive to the invisible. We study star motions, look for sudden flickers, search for gravitational microlensing events that last only days or weeks. We map the sky not just for light, but for its absence, for the moments when something dark passes through and quietly reshapes what lies behind it. One day, we may catalog them, trace their paths, understand their origins in detail. One day, we may come to know the black holes of our galaxy as well as we know the stars. But for now, they remain the unseen population, the hidden millions, the silent travelers drifting beside us in a galaxy lit by fire, but shadowed by the remnants of collapse. And as you breathe, slowly and evenly, let yourself imagine them, not with fear, but with wonder. These are not threats. They are truths. Reminders that the universe is bigger than our vision, older than our records, deeper than our understanding, and that even in the vast dark, there is movement, there is mystery, there is presence. Imagine the universe exhaling, where black holes pull, white holes push. They are the theoretical opposites, twin ideas born from the same equations, sitting at the other end of an invisible seesaw. Black holes are entrances, traps, gravity wells so deep that not even light can climb free. But a white hole, if it exists, would be the other kind of singularity. Not a place you fall into, but one you can't even approach. Nothing enters, everything exits. A fountain in reverse, pushing matter out into the cosmos, flinging time and energy outward with no regard for where it lands. Not chaos, exactly, just refusal. While black holes are silent invitations into darkness, white holes are closed doors with light leaking out around the frame. The equations allow for them. That's the strange thing. When Einstein's general relativity is laid out fully, not just sketched to match the behavior of collapsing stars, white holes slide into the margins, mathematically valid, symmetrical, unlikely. Maybe, but not impossible. They could be short-lived, they could be rare, or they could be waiting, tucked into a region of space-time we haven't noticed, distant and brief, blinking in and out of existence faster than we can focus, a possibility that hangs like fog, thin, persistent, and hard to measure. No one has seen one, not yet. No telescope has caught the outward spray of material from a point no light could reach. No signal has traced a path backward to an origin that resists entry. And yet, white holes remain, not in our images, but in our thoughts, in the spaces left behind by our understanding. Some scientists think they could be connected to black holes, forming tunnels through space-time, wormholes, bridges, shortcuts. You fall into one, and instead of being destroyed, you're expelled out the other side, into a white hole, somewhere else, or somewhen else. Of course, it's not so simple. Wormholes might collapse before anything can travel through. The passage could pinch off. The fabric of space might not hold open that long. The energy required could be immense. It could be unstable. It could be lethal. The math is a whisper, not a promise, but it whispers loudly, especially when we ask the biggest questions. What happens to the information that falls into a black hole? Where does it go? Does it vanish? Or does it reappear? White holes offer a strange kind of answer. Not a tidy one, not a certain one, but a provocative one. What if information isn't lost at all, just transferred? What if the universe has a hidden rhythm of intake and output, a balance we haven't fully understood, a cosmic inhale and exhale, cycling matter and energy through routes we haven't yet mapped? In that idea, white holes become more than mirrors. They become part of a conversation between collapse and escape, between gravity and geometry, between silence and revelation. Some theorists suggest that the Big Bang itself could have been a kind of white hole, the ultimate outpouring, a singularity from which everything emerged, impossible to approach from the outside, blasting space and time outward in all directions. It's not mainstream, but it lingers in the background of cosmology, like a strange melody you can't quite forget. If the Big Bang was a white hole, it suggests our entire universe came pouring out of something else. Maybe from the inside of another black hole, maybe from somewhere completely beyond. The idea stretches logic. That's what ideas do when they live at the edge of known physics. They stretch and blur and twist. But sometimes, when the questions get big enough, those wild ideas become necessary, because black holes themselves were once just mathematical curiosities, predictions buried in equations, unseen, unconfirmed, doubted. Now we image their shadows, we listen to their mergers, we observe the way they sculpt galaxies and distort time. So who's to say that white holes, strange, unproven, hypothetical, won't someday step out of the theoretical dark? Until then, they remain placeholders, beautiful ones. They represent a kind of hope, though not in the usual sense. They suggest that not everything collapses, that not all paths lead inward, that there might be exits hidden inside the things we think are endings. If black holes are where stories disappear, white holes are where something new might begin. They are unobserved but not unwanted, fictional but not false. They let us imagine a universe that doesn't just break things down but gives them back in some transformed, distant way. Maybe one day we'll find one, or maybe we already have and just didn't recognize it. A sudden burst of unexplained energy, a fast radio signal, a flash with no apparent cause. Something that came from nowhere, left no trail, and refused to be classified. We have lots of mysteries like that. The sky is full of them. It always has been. And in the silence between discoveries, white holes remain a possibility. A gentle challenge to what we think we know. A whisper that for every place you can't return from, there might be a place you can never reach. And maybe, somewhere in the deep dark, the universe is still exhaling. Beyond the threshold of visibility, past the edge where light gives up its struggle and time forgets how to move forward, lies a place we cannot see. We call it the event horizon. A line in space, not marked or glowing, not even truly existing as a surface, but still real in the way that rules are real. Once crossed, return is not just improbable, it's impossible. No signal, no light, no story can travel back. And whatever waits inside that border, we can't observe it directly. We can only imagine it. And imagination is both our gift and our limit. We think there's a singularity, a point so dense, so infinitely compressed, that our physics trembles and breaks trying to describe it. Not just a tiny ball of matter, but a collapse to zero. Zero space, infinite curvature, an endpoint of math itself. We don't know what infinite density truly means, only that it slips past our models like a shadow through a closed door. Some equations spit out nonsense. Others give us contradictions. Relativity says yes. Quantum mechanics says no. And there, in that disagreement, the singularity laughs quietly, unmoved. Maybe it isn't a point at all. Maybe the interior is something stranger, a folded dimension, a region of chaos, a place where space and time exchange roles and meanings. Some theories suggest a firewall of energy, a violent, burning edge that would incinerate anything falling through, a final, blazing warning that the universe is about to stop making sense. Others whisper of a bounce, that instead of a collapse to nothing, the core rebounds somehow, like a heartbeat of space-time itself, a miniature Big Bang forming something new on the other side. But these are theories, equations dressed as guesses. No experiment has tested them. No probe has returned with data. Once something crosses the horizon, its story ends, at least from our perspective. And perhaps that's the most unsettling part. Not that we don't know what's inside, but that we may never know. That the center of a black hole is a place not just beyond vision, but beyond meaning. Beyond the idea that space has places at all. Inside the event horizon, time doesn't behave. It bends and buckles, rushing forward for the falling object while freezing from the outside view. To the one falling in there is motion, descent, change, but to us, still, distant. They never arrive. Their image lingers forever at the edge, stretched and dimmed by redshift, paused just above the boundary. From out here, the fall never finishes. From in there, it's already over. What's most haunting is the quiet. Not the roaring collapse or the imagined violence, but the stillness. Once something enters, there is no more reaching, no echo, no retrieval. The event horizon isn't a wall, but a silence. A one-way silence, absolute and indifferent. And that silence challenges more than physics. It pushes at the edges of philosophy, of identity, of continuity. What happens to the matter that enters? To the information it carries? To the laws it once obeyed? Does it vanish? Is it scrambled beyond recognition and slowly radiated away as Hawking predicted? Or is it preserved somehow, etched onto the surface in a cosmic ledger too subtle for us to read? The black hole doesn't answer. It only waits, massive and mute, the keeper of secrets we aren't yet wise enough to hold. Inside the event horizon, our understanding dissolves, our maps end. The smooth curvature of space-time becomes a knot we can't untangle, a page where the ink runs too thick to read. It's not just about gravity or mass. It's about the limits of knowing. The idea that some places in the universe are so radically removed from our experience that even our best tools, our logic, our instruments, our mathematics, can only circle them like moths around a dark flame. And yet, we're drawn to it. That unseen center calls to our curiosity with a power equal to its gravity. We send our minds there, if not our machines. We build simulations, sketch diagrams, imagine the fall. We ask what it would feel like to pass the edge, to enter the quiet, to be pulled towards something that isn't a place but a fate. And though we can't answer, we keep asking, because black holes aren't just objects, they're questions. They sit in the sky like punctuation marks at the end of unspeakable sentences. And the event horizon is where the sentence breaks off mid-thought, leaving only the darkness beyond. A pause not of speech, but of possibility. Inside, maybe space becomes time. Maybe dimensions loop in on themselves. Maybe there's nothing at all. Not in the sense of emptiness, but in the sense of erasure, a cancellation. The end of all coordinates, the final surrender of shape. Or maybe the inside isn't empty. Maybe it's full, not of things, but of meaning we don't yet have the language to describe. A hidden script written in gravity and paradox, waiting for a new kind of reader. Until then, we stand at the edge. We build equations like bridges, knowing they'll never quite reach the other side. We measure what we can. We imagine the rest. And in that imagining, we find something important. Not answers, but awe. Not certainty, but the beautiful ache of unknowing. And so we continue, looking into the dark, wondering what waits in the heart of silence. There's a rule in quantum mechanics, ancient in its authority and endlessly tested. Information cannot be destroyed. The arrangement of particles, the structure of matter, the blueprint of what a thing was and how it came to be, it all persists, somewhere. Even when objects burn, dissolve, or shatter, the patterns they once formed remain etched into the fabric of reality. Maybe scattered, maybe hidden, but not erased. The universe, it seems, keeps its records. And yet, black holes challenge that truth. Because a black hole doesn't merely swallow matter, it erases its past. From the outside, all we can observe is the mass, the spin, and the charge. Everything else, every detail about the shape, structure, or identity of what fell in, is lost. A star, a planet, a poem, a person, once across the horizon, all are reduced to sameness. Just weight, just pull. The black hole remembers how much you weighed, nothing else. And that's where the paradox lives. General relativity doesn't mind. To Einstein's theory, this is fine. The black hole's identity is only what we can measure from the outside, and all the rest. The tangled complexity of what once was doesn't need to survive. Gravity is simple like that. Unforgiving, but honest. But quantum mechanics objects strongly. It insists that the universe must be reversible, that if you rewound the film of time, every atom could find its way home. Nothing truly disappears, not even in principle, which means that if a black hole takes something in, it can't simply destroy the information that came with it. It must do something with it, tuck it away, encode it, leak it out, but we don't know how. This contradiction, this fracture between our two best theories, is called the black hole information paradox. It's one of the deepest mysteries in modern physics, and it isn't just about black holes. It's about reality itself. It asks whether our universe is fundamentally knowable, or whether there are places where the rules stop working, where the narrative of a thing can be deleted forever without a trace. Stephen Hawking shook the world when he showed that black holes aren't entirely black. That, through a strange quantum process near the event horizon, they can slowly radiate energy, not from inside, but from the fuzz of uncertainty right at the edge. This Hawking radiation is faint, slow, and nearly impossible to detect. But it means black holes aren't eternal. They can shrink, they can fade, and eventually they can vanish. But if they vanish, where does the information go? It seems to be missing from the radiation itself. The particles that escape carry no imprint of what fell in. They're generic, random, as though the whole is sweating out heat without memory. And if the black hole disappears completely, taking all that unmarked radiation with it, then the information is gone, which quantum mechanics says cannot happen. So physicists are caught between giants. One theory, powerful and elegant, tells us how matter bends space-time. The other, subtle and strange, governs the smallest particles with astonishing precision. Both are correct, and yet, here, they collide. And in that collision lies a possible key to unification. Because if we can resolve this paradox, we might uncover the long-sought bridge between gravity and quantum mechanics. We might glimpse the theory that underlies everything, not just black holes, but the universe itself. Ideas have been proposed. Some suggest that the information is somehow encoded on the event horizon, smeared across the surface like a cosmic ledger, that it's never truly inside, just recorded at the boundary, preserved as the whole shrinks and evaporates. This is the holographic principle. The idea that all the information inside a volume of space can be described by what's on its surface. A radical thought, but one that echoes through cutting-edge physics. Others think that the radiation itself carries subtle correlations, too subtle for our crude instruments to detect, but present nonetheless. That the randomness is only apparent. That if you could collect every particle emitted and analyze them with infinite care, you'd find the story, encoded in heat, hidden in noise, but whole. Still others invoke exotic concepts, firewalls of energy that burn away information at the horizon, or wormhole-like connections that thread inside the hole to other parts of the universe, preserving continuity in ways we cannot yet visualize. Each theory has its beauty, each one its cost, but the truth is, we don't know, and maybe we never will. Because to test these ideas, we'd need to gather the Hawking radiation from a black hole, all of it, and measure it with precision beyond our current reach. It would take billions of years. It would require waiting for something that hasn't happened yet, and might not happen anywhere near us. Our technology, our lifespans, our species may not last that long, but the question remains, shimmering at the edge of knowledge. Do black holes destroy information, or do they hide it in places we cannot yet see? Is the universe a ledger, perfectly balanced and never forgetting, or are there true abysses, not just in space, but in knowing, where memory is swallowed whole? It's strange to think that some of the smallest particles, flickering at the edge of existence, could hold the answer to such a cosmic question, that a tiny twitch of quantum uncertainty, playing out near the mouth of a black hole, could teach us whether the universe is lawful or broken. But this is the frontier, not just of science, but of imagination, because the paradox isn't just technical, it's philosophical. It touches on what it means to preserve identity, to maintain continuity, to believe that the past is knowable, and the future, in some sense, just an unfolding of what came before. Black holes challenge that belief. They sit in the night sky like riddles, daring us to reconcile fire and ice, order and collapse, structure and silence. And in the echo of their paradox, we hear not just a scientific question, but a human one, about what it means to be part of a story that continues even after we're gone, about whether the record of what we were, our thoughts, our atoms, our motions, is permanent in the fabric of space, or if it, too, can be lost to the dark. The black hole doesn't answer, but it invites the question. They would be small, not city-sized, like the stellar remnants we've charted, not monstrous like the hearts of galaxies. These would be microscopic, or maybe the size of a mountain, or maybe something in between, depending on when they formed and how the early universe sculpted them. Not born from dying stars, but from pressure itself, from chaos, from density and heat so intense that space could fracture under its own newborn weight. These are primordial black holes, hypothetical children of the Big Bang. In those first brief moments after the universe began, everything was energy. Matter hadn't yet settled into atoms, or stars, or galaxies. There was no structure, just searing heat, quantum fields, and fluctuations rippling through space like shivers across skin. Some regions were denser than others, some more compact, and for a blink in cosmic time, that difference may have been enough. If a region compressed just slightly beyond a certain threshold, it could collapse, not into stars, because those hadn't yet formed, not into galaxies, because gravity hadn't had time to gather, but directly into black holes, tiny ones. Unlike the ones we study now, these wouldn't come with supernovas or violent deaths. They would just blink into being, squeezed into existence by the raw mechanics of expansion, trapped forever, or at least until Hawking radiation slowly eats them away, bit by bit, over eons far longer than the age of our universe. They would be ancient, older than any planet, older than any light still traveling through the sky. If they exist, they are fossils of the cosmos itself, not made from something, but made with everything, embedded in the earliest chapters of reality's formation, carrying no memory but mass, no identity but presence. They would drift through galaxies, slide through solar systems, pass through planets, perhaps even through you, unnoticed, because they would be dark, so small that no telescope could see them, so quiet that no radiation would betray them. Not even the gravity they wield would be enough to give them away, unless they passed close, very close, to something we could observe. A star flickering, a planet trembling, a stream of matter pulled slightly off course. Tiny black holes could be everywhere, hidden in the margins of what we call nothing. Some scientists wonder if they're part of the answer to another great mystery, dark matter, that invisible scaffolding that holds galaxies together, that outweighs visible matter by 5 to 1, but doesn't glow, doesn't burn, doesn't reflect or shine. We only know it's there because of what it does to everything else. And maybe, just maybe, part of it is made of these hidden black holes, not particles, but punctures, not matter, but gravity. We don't know. No one has seen a primordial black hole. There is no direct evidence, only equations and clues and hints from the way galaxies behave. The idea is beautiful, but fragile. It depends on how the early universe behaved in its first fraction of a second, and we cannot go back there. We can only simulate, only guess, only test the consequences. But the consequences are wild, because if they exist, they are still here. A black hole the mass of a mountain would be smaller than an atom. It could pass through Earth without resistance, falling in from the sky, exiting out the other side, and leaving barely a whisper behind. And yet its gravity would be intact, its mass unchanged, a hole, invisible and complete, slipping silently through rock, water, bone. And if one passed near a star, it could start to feed. It might glow, briefly, if it began to consume, and that glow, that flicker of X-rays or plasma, might be the only way we ever catch one, by accident, by luck, by watching everything and hoping something flickers the wrong way. Primordial black holes would be survivors. Most of the chaos from the Big Bang has cooled, expanded, or combined into structure. But these would still be solitary, still unaltered, still roaming the universe as it ages around them. They might be traveling through the outskirts of galaxies or slingshotting between stars, moving in orbits too vast for us to see. Or closer. The Earth moves through the galaxy, and the galaxy moves through clusters, and those clusters move through filaments that thread across the observable cosmos. Along the way, we pass through dust, comets, particles, radiation, and maybe, once in a while, something else, something small and ancient, something that curves space as it passes, bends it just slightly, then moves on. And we wouldn't know, not unless we had the perfect instruments in the perfect moment, aligned by chance with the path of a relic older than atoms. It's possible, some say, that one of these passed near us in the past century, that a strange microlensing event, a brief brightening of a distant star, was its signature. One blink, one anomaly, a footstep in a darkened room. We don't know how many there would be, maybe millions, maybe more. If they formed in the early universe, their number could be staggering. Or maybe they never formed at all, and the cosmos took a different path. Maybe the equations that predict them are elegant but wrong. Maybe gravity had other plans. But the possibility is haunting, that all around us, scattered like ashes from the fire of creation, are tiny reminders of how the universe began. Not stars, not planets, not galaxies, but voids. Ancient, perfect, unyielding, and if we ever catch one, it will be like reading the first word of a forgotten story. One written in heat and pressure and silence. A story that began not with life or light, but with collapse. And in that collapse, a clue, a signature, a whisper from the moment everything became something. Maybe the end is not the end. We think of a black hole as a destination, a final place, a cosmic full stop, the ultimate collapse. A star runs out of fuel, falls inward, crushes itself under its own weight, and vanishes behind a veil of no return. But that's only the view from this side. From where we sit, outside, observing, from a universe with edges and laws that seem familiar, consistent, maybe even complete. But what if that's only half the story? Some theories suggest something astonishing, that what we call an ending might, somewhere else, be a beginning. The singularity at the center of a black hole, that impossible point of infinite density where our mathematics unravel, might not be a point at all. It might be a bridge, a fold, a pinch in the fabric of existence so intense that it tears not just space, not just time, but the boundary between realities. If our universe was born in a bang, a furious expansion from a singularity, then perhaps every black hole is its own tiny echo of that first fire, a reverse explosion, a collapse here, an expansion there. Maybe when a star dies in this universe, a new universe is born in another. Not figuratively, not poetically, literally. A black hole in our cosmos could be the mouth of a tunnel, and on the other end, beyond what we can see or measure, a whole new space might be inflating, new physics, new dimensions, a fresh slate of particles and forces cascading outward from a point of origin that began as a death cry in ours. It's called the multiverse hypothesis. One version of it anyway. Not a single lonely universe, but a vast, possibly infinite collection of them. Universes that birth more universes, endlessly. Not side by side like bubbles in foam, but nested. A black hole in one might contain the seed of another, and inside that, more black holes. More births, more branching paths of physics and time. In this view, our universe might not be the first. It might not even be particularly special, just one of many children in a lineage that stretches backward beyond memory. Our own Big Bang could have been the bloom of a black hole in a parent cosmos long gone. A quiet collapse there sparked everything here. Their star died, and our sky was born. This idea isn't science fiction. It lives in the math, in the theories that try to reconcile gravity with quantum mechanics. Some cosmologists believe that black holes might allow information to escape, not into our own space, but into another. That singularities are not infinite, but transitional. That every time space is crushed in on itself, somewhere else, it is unfurling. It's almost too big to comprehend. Think of how much exists inside our universe. Trillions of galaxies, each with billions of stars, each surrounded by worlds and dust and heat and light, a staggering volume of being. Now, imagine that all of it, every field and law and form, came from the throat of a black hole in another universe, that all of it sprang from a collapse, spun outward like breath from silence. And we might be doing the same. Every black hole in our sky, every invisible singularity hiding behind an event horizon, might be in the act of creating. We don't see it. We can't. For us, it's a boundary. But just beyond that boundary, beyond where our instruments and theories begin to fail, there could be inflation. An entire universe, blooming unseen, expanding from a point into vastness, its own stars, its own laws, its own time. There might be no way to know. No signal can escape a black hole. No probe can cross the horizon and return. If our black holes contain other universes, they are closed to us, locked away. Each one might be its own self-contained cosmos, with no threads back to the one that birthed it. But in theory, they could remember. The imprint of their origin might remain in the structure of their physics. A faint memory, etched into constants and particles and rules. And if they remember, maybe so do we. Maybe the reason our universe behaves as it does is because of what came before. Because the black hole that birthed us had its own conditions, its own gravity, its own tempo. And those traits carried over, not as matter, but as pattern. Some theories even suggest a kind of cosmic evolution, that black holes capable of producing universes pass down traits like genes, that universes with more black holes produce more children, and over time, a kind of natural selection favors the proliferation of certain constants, certain architectures of space and time. That would mean our universe is not just an accident. It's the result of a long lineage of cosmic births and deaths, a family tree with black holes as branches and singularities as seeds. We might be descendants, unknowingly shaped by the physics of other places, other ages, and the cycle continues. Each collapse might give rise to something entirely new, not a clone, not a mirror, something utterly foreign, a universe without stars, or one without atoms, or one where time flows sideways, or not at all. Maybe some die instantly, maybe some never stabilize, but some expand, some survive, some grow, and in those, maybe someone else wonders too. Maybe they look into their sky and see the mouths of black holes and wonder what came before them, what waits behind the dark. Maybe they have their own theories, their own quiet awe, their own bedtime stories built from math and mystery. Maybe we are someone else's black hole. Maybe our entire universe is an answer to a question we'll never hear. Before a black hole is born, there is a death that lights up the sky. A massive star burns for millions of years, fusing lighter elements into heavier ones in its core. Hydrogen becomes helium, helium becomes carbon, then oxygen, silicon, iron. It fights against collapse by producing light and heat, pressure that pushes back against the weight of its own gravity. But eventually, the fuel runs out. Iron is the limit. It cannot be fused to release energy, and when the core becomes mostly iron, the balance breaks. The star falls in on itself in a final, furious moment. The core collapses faster than thought, in less than a second, and the outer layers, now unsupported, crash inward. What follows is violence on a scale that rewrites space. A supernova. Not just an explosion, but a detonation so immense it briefly outshines an entire galaxy. In that moment, in the crucible of destruction, elements are born. Heavy elements, gold, platinum, uranium, the stuff that doesn't come from ordinary fusion but from shock and heat and collapse. The periodic table, beyond iron, is written in supernova fire, and some of that matter becomes you. The calcium in your bones, the iron in your blood, the gold on your finger. These did not form in gentle processes. They are the remnants of stellar violence. They are the leftovers of death. The ashes of ancient stars that lived and died before the Earth was even a whisper in the dark. The atoms in your body are billions of years old, recycled through space, drifting and scattering, carried by winds and waves of energy across light years until they found their way here. Every breath you take is made of pieces of stars, and not just stars, but stars that died with such power they created black holes in their wake. The most massive of them did not die quietly. They collapsed so completely that what remained fell inward forever, past the point of return. The light from those stars is gone. Their surfaces are gone. Their names, if they ever had them, are lost to time. But what they left behind, that's not gone. You are what they left behind. There's iron in your blood that was born in a supernova. That iron exists because a star lived long enough to build it, and then died fast enough to release it. A black hole may have formed from the same collapse, pulling inward everything too close, too slow, too unlucky to escape. But not everything was captured. Some material, a fraction, a shell, a shock wave, escaped, and that material seeded the galaxy. It drifted into clouds, and those clouds became new stars, and around those stars, planets, and on those planets, life. It's possible that you are made of atoms from many different stars, that your body is a mosaic of cosmic funerals stitched together over eons. One particle here, another there, mixed and remixed as the universe churned forward. You are, quite literally, stardust. That phrase is not a metaphor. It's a map of your origin. You are the echo of collapse. Black holes don't just swallow. They create the conditions for creation. By ending the life of a star in a supernova, they help scatter the elements necessary for planets and people. Without those explosions, the universe would be hydrogen and helium, light and lifeless. No carbon, no nitrogen, no phosphorus or potassium, no skeletons or neurons or oceans or songs. The cycle is elegant and cold. A star is born, lives, burns, dies, and either becomes a black hole or a different kind of remnant. If it becomes a black hole, it often does so violently, flinging its enriched guts outward first. Those guts become new stars, new planets, and eventually, beings that can think about all of it. Beings like you. You are part of the feedback loop of the cosmos, part of its memory, its aftermath, and the black hole that formed from that death? It's still out there, silent, invisible. It does not know what it left behind. It cannot see you. It cannot care. But its existence made yours possible. And in some distant corner of the galaxy, you and it are bound by origin. You are the leftover light, the escaped heat, the matter that slipped away before the darkness closed. It's a strange kind of kinship. Black holes are the most extreme form of gravity. You are built from the things gravity once held, and gravity still holds you, to the earth, to the sun, to your own memories and heartbeat. You are pulled by it, shaped by it, dancing in orbits written billions of years ago. But you are not falling in, not yet. You are still outside the event horizon, still able to think about these things, to lie still and wonder, to hear stories that connect collapse with breath, silence with music, the end of a star with the rhythm of your lungs. You are made of ancient violence, and yet, here you are, soft, breathing, dreaming, holding a body that used to be part of something burning at 10 million degrees, fingers made of former stars, a mind that can imagine the death of suns and the birth of time. You are the beauty left behind by black holes, and that beauty, somehow, knows its own name. At the very center of our galaxy, past the spiraled arms and dusted bands of starlight, there waits something immense and invisible. It does not shine, it does not speak, it does not stir, and yet, its presence holds us all in place. Everything you see when you look up into the night, every constellation, every glinting memory of fire, is slowly circling it, quietly, eternally. Sagittarius A star, 4 million times the mass of the Sun, compressed into a region so small it could fit within the orbit of Mercury. It doesn't blaze like the stars. It doesn't flicker or pulse in a way the eye can see, but it pulls. It always pulls, and we move to its rhythm. You are part of that orbit. So is the Earth. So is everything we've ever known. We don't spiral into it, not now. We keep a careful distance, balanced between motion and gravity, speed and surrender. The galaxy is a grand, slow dance, and this silent partner in the middle sets the tempo. And yet, most nights, you wouldn't even know it was there. You walk beneath the stars, the same way people have for thousands of years, and you feel only the wind, or the pull of the moon, or the ache of your own thoughts. You see the glow of distant suns and wonder what's out there, maybe, but you don't feel the great gravity at the core of it all. You don't feel Sagittarius A star, but it's there, not in a loud way, not like a storm or a fire. It is quiet, constant, and utterly indifferent. It doesn't reach for us with intention. It doesn't want. It doesn't need. It simply is. Its pull is soft in a way only vastness can be. The kind of softness that comes from inevitability, from having all the time in the universe. It waits. It has waited since long before Earth cooled, long before life swam, or climbed, or built cities and stories. It will wait long after. It does not demand to be noticed, and still, it holds the galaxy together. That kind of presence, the invisible kind, isn't just out there. It's in you too. The same way Sagittarius A star pulls on stars without being seen, you carry mysteries that shape your own orbit. Quiet thoughts, old questions, griefs you don't name, hopes you whisper only in dreams. They sit somewhere deep inside, not asking for attention, not flaring into view, but they're there. And they guide you. You don't always have to name them. You don't have to drag every part of yourself into the light to know it's real. Some things are too deep for words. Some truths are like black holes, impossible to touch directly, but undeniably powerful in their influence. Maybe you've felt that. Maybe you've had nights where you sensed something vast and wordless pulling at the edges of your mind. Not in fear, not in sadness, just a stillness. A sense that something deep beneath the surface is holding it all together. The strange thing about black holes is that their edges are fuzzy in time. If you were watching someone fall into one from far away, you'd never see them cross the event horizon. They'd slow down, redshift, dim, and seem to freeze just outside the boundary. To you, they'd never truly fall. But from their perspective, they would. That's the paradox. Two truths, both real. Two views, both incomplete. That's what it means to live in a universe shaped by relativity. And maybe that's what it means to live, period. That we are always holding two versions of things, the one we see and the one we feel, the story we tell and the one we carry quietly inside. In the end, the story of black holes isn't about destruction. It isn't even about death. It's about what remains, what continues, what endures in silence, at the center of all motion. Sagittarius A star doesn't roar. It doesn't devour constantly or throw tantrums of light. It simply is a point of gravity, a dark heart that holds billions of stars in orbit, not through force, but through constancy. And maybe that's a kind of peace. We often think that the things which matter most must be visible, loud, declared. But sometimes, the most important things are the ones we cannot see, the ones that don't ask for attention, the ones that simply shape everything around them, quietly, patiently. You don't always need to understand something to honor its presence. Some mysteries are not puzzles to be solved, but places to sit with, like the curve of a question mark drawn in the stars, like the hush that comes just before sleep, like the pull you can't name, but feel all the same. The journey through black holes is not about answers. It never was. It's about awe, about drifting into the strange and the infinite, and letting yourself wonder. It's about resting in the space between knowing and not knowing, about being okay with silence. And now, here at the end, all the noise fades, all the facts, the paradoxes, the fire and fury, the collapse and birth, they fall away, like stars slipping beneath the horizon. What's left is gravity, stillness, a quiet pull. You orbit it already. You always have.